So x-axis symmetry means that the y values are going to change. Does everybody understand that? When you have y-axis symmetry, so when you go across the y-axis, what happens to xy when you go across the y-axis? How does that change? What changes? X has become what over here? Negative. So you get a negative x, positive y, right? And then when you have origin symmetry, so when you go across the origin, you get, what changes in the origin symmetry? Well, now xy becomes negative x, negative y. So here's how symmetry is going to work. In order to identify symmetry, you can look at the graph. When we go to verify symmetry, you're going to pick points on the graph. For instance, with x-axis symmetry, you're going to pick a point. If a graph has x-axis symmetry, you should be able to reflect that point and the y value change. You understand that? If a graph has y-axis symmetry, you should be able to reflect that point and the x-axis change. If a graph has origin symmetry, you should be able to reflect the point and both the values change. I got that? And when I say change, your signs are just changing. So essentially what you have is this. In the x-axis symmetry, the point xy becomes, the only thing that's going to flip now is the y value. So y values change. In y-axis symmetry, the point xy, the thing that flips now is the x values. And in origin symmetry, the point xy flips both the values. So if you look at the graphs you have here, I want you to take this first function here. Take that first function, and I want you to give me the x-axis symmetry of this function, the y-axis symmetry for this function, and the origin symmetry of this function. And we're going to do that by identifying the points on the original function and using our rules to flip those points now. So this point is 0, 0. This point is 4, 7. This point is 7, 0. And now again, starting with x-axis symmetry. If a graph has x-axis symmetry, how do the points change? Well, this says that the coordinates go, what flips this time? The y's flip their signs, right? That's what this means. So your y values are going to flip its sign. So 0, 0 will remain the same. 4, 7 becomes what? 4, negative 7. The y value changes its sign, so that's 4, negative 7. And 7, 0 becomes what? 7, 0. It doesn't change, because the y is not going to change if it's 0. So you get this graph. Bless you. Is this a reflection across the x-axis of this function right here? Yes. So that's good. In y-axis symmetry, what happens in y-axis symmetry? Who changes signs now? X values change their signs. So 0, 0 stays the same. 4, 7 now becomes what? Negative 4, 7. And 7, 0 becomes negative 7, 0. So we get this function. Is this a reflection of the original function across the y-axis? Yes. And then in origin symmetry, here's what happens in origin symmetry. Both of the signs are going to do what in origin symmetry? Change. So 0, 0 stays 0, 0. 4, 7 becomes what now? Negative 4, negative 7, right? And 7, 0 becomes negative 7, 0, so you get this function. Is this a reflection across the origin then, of the original function? Yes. We understand this process, right? What I want you to do is do it for this function now. Find the x-axis symmetry, the y-axis symmetry, and the origin symmetry for this function. Find that your graphs are looking like my graphs right now. And again, this is a very simple process. The first one, the purple one, my x-axis symmetry, the only thing that's changing are your y values. So your x's stay the same, the y's flip their signs. And the second one, the thing that's changing now is your x values, because you're going across the y-axis, so it's going to mean that you get your x's change their signs, the y's remain the same. In the last function, what you're doing to your x's, you're flipping your x's around, and you're also flipping your y's around. So here you're going to go to negative x, negative y. We understand that process, right? So symmetry is a very simple thing when you're looking at it from a graph. And you can identify symmetry by just picking points on the graph and comparing the points. All right? The other thing you need to know how to do with symmetry is test for it, though. And so when you test for symmetry, there's two types of symmetry you can actually test for. You can only test for the symmetry that's going to allow it to be a function to begin with. So that throws one of the types of symmetry we have out the window already. That's going to be x-axis symmetry. You can't test for x-axis symmetry. So when you test for x-axis symmetry, you have two vertical lines, so it's not going to make it a function. So anything that has x-axis symmetry is not a function. All right? So we can't test for it. We can test for it, though. And we are going to test for here's how we test for symmetry. For y-axis symmetry, here's what you need to know. A graph has y-axis symmetry, or a function has y-axis symmetry if f of 1 is equal to f of negative 1. If f of 1 is equal to f of negative 1. What does this mean? What does it mean when I say f of 1? X is 1, right? What does it mean when I say f of negative 1? So what this means, though, is that if f of 1 is equal to f of negative 1, then you have y-axis symmetry. Well, f of 1 also represents this entire thing right here. What else can we call this right here? This entire thing? Y. So this entire thing, what can we call this? Y. What does that tell me then? If I plug in f of 1 and it equals f of 1, if it equals f of negative 1, or if y equals y, that means I have x-axis symmetry. That means if both these values are the same, I'm going to get x-axis symmetry. If I go and test for origin symmetry looks like this. If f of 1 is equal to negative f of negative 1, then you have origin symmetry. Well, what does this mean? Good. If y is equal to negative y, or if they're opposites, I have what is known as origin symmetry. So it's a very simple test, because all you have to do is evaluate and look at the numbers. So here's an example. Take the function f of x is equal to x to the fourth plus 2. The graph of x to the fourth plus 2 looks something like this. Looks something like this. Looks like a W, basically. So from this we see that it has what kind of symmetry? It should have y-axis symmetry, right? Let's test for it. Here's how you're going to test. You're going to plug in f of 1. When I plug in f of 1 into that function, x to the fourth plus 2, what is that equal to? Well, what's 1 to the fourth? What's 1 plus 2? 1 plus 2 is 3. Plug in negative 1. What's f of negative 1 equal to? Well, it's negative 1 to the 4th. What's negative 1 to the 4th? What does negative 1 to the 4th mean? I'm multiplying negative 1 by itself how many times? 4 times. So what's negative 1 times negative 1? What's 1 times negative 1? Negative 1. What's negative 1 times negative 1? So what is negative 1 to the 4th equal to? And then what's 1 plus 2 again? Do you see how I get the exact same y values when I plug in 1 and negative 1? What does it tell me about this function then? It's what kind of symmetry does it have? Y-axis. Another way to look at it, you can write these as points. This is the point 1, 3. This is the point negative 1, 3. Which value changes sign? Which value changes sign? X. When the x values change their sign, what kind of symmetry do you have? Y-axis. You understand that? So look at the origin. Let's try this function. F of x is equal to x cubed minus 2x. So if I do x cubed minus 2x, I get this. F of 1. Evaluated f of 1. What's 1 cubed? 1, right? And then I do minus 2 times 1 is what? 2. So that's 1 minus 2, which is negative 1. If I do f of negative 1, what's negative 1 cubed? Negative 1. So that's negative 1. Then you have 2. You have a negative 2 times the negative 1 makes it a. So that's negative 1 plus 2, which is what? 1. Look at the signs of these. They're what? Opposites of each other, right? Y'all see that? So if they're opposites, that means you have origin symmetry. You can write it as a point again. You have 1, negative 1. You have negative 1, 1. What happened to the signs on the second part of this right here? Well, the 1 became a negative, and the negative 1 became a positive. So both the signs flip, right? What kind of origin makes both signs flip? I mean, what kind of symmetry makes both signs flip? Origin symmetry. Does everybody understand that? X-axis symmetry. X-axis symmetry cannot be tested for. Cannot be tested because there is no function. And the other thing you need to know is this, if f of 1 does not equal f of negative 1, the graph does not have symmetry. And that's with the exception of this right here, the exception of the origin one. But just in general, if you plug in a number, you plug in 1 and negative 1, and you get two totally different numbers, the graph doesn't have symmetry, all right? Are there any questions on this? You're okay with that? So look at the homework real quick. Let's talk about that. Here's what I want you to do on the back part. Look at problem number 7 on the back. What you're going to do first is just look at the graph and tell me what kind of symmetry it has. Can you look at the graph and tell me what kind of symmetry that has? X-axis symmetry. There, y'all see that? Everybody understand that part? Then you're going to support the answer numerically. Numerically means picking points. So pick a point on the graph. For instance, I picked the point 1, 2. Does everybody see that? If it has x-axis symmetry, what other points should be on the graph? If 1, 2 is on the graph, then x-axis 1, negative 2 should be on the graph. Is that on the graph? So that verifies it numerically. I understand that. And the last part says to confirm it algebraically. Well, because it has x-axis symmetry, can you confirm it algebraically? No, because it's not a function, right? Look at 8. Can you confirm that? Can you confirm this algebraically? Look at it again. No, because it's not a what? It's not a function. It has x-axis symmetry, right? It also has what kind of symmetry? Y-axis as well. It might even have origin symmetry as well. Check that. Can you confirm 9? Yes, because 9 is a what? Function. Can you confirm 10? Because it's a function. 11, can you confirm it? 12, can you confirm? No, it's not a function. You understand that? So you can only confirm algebraically 9, 10, and 11 for this paper, all right? I want you to confirm those algebraically. The other ones, don't worry about it. Don saying don't do them. Don't confirm them algebraically. Don't worry about trying to confirm it algebraically, all right? Any other questions? Y'all okay with this? You have a quiz on Friday. Quiz is on Friday, all right? Quizzes mean you don't use the homework. That's the only difference. And it'll probably be a little bit harder than the homework check. So I'll get those homework checks back to you tomorrow. Any questions? All right, then y'all go get started on homework.